Here, let's start with the chapter 9, and which is the last chapter in this class, and hang on there, almost there. This chapter is talk about the deflections of beams, and deflection, that means the vertical displacement of the beam under loading. So which means we simply want to know how much a beam is deformed and its displacement in the vertical directions. And so here in these slides we have 5 sections and to explore. And so we will start with the equations of deflection of beams. And to proceed, and you must have a knowledge on solving differential equations. Here is the ordinary differential equations, and solving those equations by integrations. An example here I give here is highly relevant to what we're going to see in the contents of diffraction of beams. For example, here we think we look at the second order differential equations, and which dy the square dx squared equal to minus px. And so here if we do the first integral, and so from here to here you integrate the both hand side with x, and you will get this equation. And then you integrate one more time, you will get these equations. And along with each integration, there's a one integration constant coming up, C1 and C2. In total, here we have 2 integration constants, and which can be solved with appropriate boundary conditions. So here I won't review the differential equation, the solution process. If you have kind of something you need to review, please on your own, and before you proceed these sections, otherwise you're going to get lost. Okay, so let's take a look what is the deflections. So here I'm showing here that is the beam under deformed from his original. So here I'm drawing his original undeformed shape. Okay, so once the beam is bent, then it will deform. So basically here the deflection simply, for example, if we look at this point here, and this is a point after deform, so that is a deflection here. So here I'm showing is a deflection. For this case, deflection is downward. Okay, and for example here you can look at here this point, and it deflect to here. So basically at that point it deflect to that much. So for example, let me call the point A and the point B. So in general, the deflections in the beam is different, depends on which point you're interested. For example, at this point, that is clamp side, deflection should be 0. Okay, and on the other side, we also interested in knowing, in addition to the deflection, we also sometimes interested in knowing the slope. And for example, at point A here, the slope, I simply draw a tangent to the curve of the beam. So this is the tangent here, that is a slope here. And at this point B here, I draw the tangent line, and the slope of this tangent line, that is a slope here. Okay, so anyhow, we back to okay, here one more notation here, and rho b, this called the radius of curvature. And because we know any curved structure, any curved line, or I would say any curve, they always have the curvature there. And once we have a curvature, we can always determine the radius of a curvature. So basically here 1 divided by rho, and in general say this rho representing is the radius of curvature at particular point B here. Okay, so let me check, this is point C. Okay, in general, the rho is the radius of a curvature, and this one give us simply is the, we call the curvature. Okay, so that's kind of the geometric information here. And then in general, we can see the we have this formula. So basically curvature equal to the bending moment divided by EI. And probably some of you have gotten these equations, but basically this equation is from our chapter 4 when we talk about the pure bending. And if you have time, probably you can dig out the slides of our chapter 4, and this equation appeared at the very beginning of the chapter 4 there. Okay, so we start from here, and on one side, the right hand side, that is about the loading informations, and also about the material informations. Loading information basically is expressed through this term mx. The material information basically is expressed by E and I representing is a moment of inertia of the beams, and E is a Young's modulus. Okay, on this side, the left hand side, that is the curvature. Basic curvature is the geometric info. Okay, so basically this equation, that's a kind of the information here, and so once the material is bent, it's deformed, and it deformed, basically it changed the geometry. So that is the equation for this case here. And for example, here we consider a cantilever beam, and just for this case, so let me see how can we do it. So basically here for cantilever beam, let me redo the things here. So this is the beam here, okay, and then under the point loading here is P. So here we can refer to try to draw the shear and bending moment diagram to see how can we dig out the loading informations. So the first one, we find out the reaction here, that's a P. So now with that information ready, we can begin to draw the shear and bending moment diagram. So this is 0V, this is 0N. Again, here, if you forget how to draw the shear and bending moment diagram, refer to our discussion in chapter 5 there. Okay. So along the sign conventions of when we draw the shear bending moment diagram, then we can see. So for this case, you can see for this beam is pretty much constant. Okay, the shear and bending moment diagram, that is the sign conventions. Okay, so for this case, this is negative. Okay, there's a minus P here. And for bending, and the free end is starting from 0, and then at the reaction here, and we have reaction bending. Sorry, let me change color. So this is a reaction bending. Okay, M equal to minus P L. So for example, if the whole length is L. Okay, so starting from 0 and ended up is minus PL, and with the slope equal to V, so that is this case. Okay, so this is minus P. So for example, if we want to look at any locations, so let me assign my coordinate systems. For example, here is the X and here is the Y here. So at any locations, for example here, say at this point, the distance from the origin is X, so that corresponding to here, that location is X. So by this case, you can see the moment as a function of X equal to minus Px. Okay, so basically from here is minus Px. So you plug in here the M over X equal to minus Px, and that is the one here. Okay, so for this case, regarding the loading information, and that basically you can use whatever the methods we've been discussed in until now in this class, okay, and try all the methods you like. And I prefer is the shear bending moment diagram because that is more efficient. Okay, and usually the E and I, that is the material information, usually those are given, or you can very simply and quickly calculate it or determine it. So now the issue is this, and the right hand side we basically have no problem. So basically for the right hand side information, that should have no problem here, and assuming you have been doing well. Okay, and now the issue is how do we deal with the left hand side, the geometric information. So that is the main purpose of this section. We're going to dedicate our time, remaining time, to get more understanding of what this term means. And so before we're doing that one here, we can utilize one more equation example to demonstrate how do we determine the equations of the deflection of the beam. So here we use look at this example, and step one is again just follow my previous method. I'm going to try to use the shear and bend moment diagram. So first one, determine the direction AC, and then begin I can draw the shear and bending moment diagram here. Okay, so here is X and V, and X and M. Okay, so here is our exercise. One more time, drawing the shear bending moment diagram, and then from here this is our sign conventions. Positive for shearing. Okay, so now we determine this one. So here this one is positive starting from 1 and 1 kilonewtons. Okay, and then constant, and to here we have 4, so downward by 4, so this is -3, and constant, and now upward by 5, so here up to from -3 to 2. Okay, then keep constant and to 2 here. Now the moment at the free end, so this is called the free end. Okay, so the both ends are free end. At the free end, the moment equal to 0. Keep this in mind. So we start from here, ended up 0 here. So here the slope equal to the V. V is constant, so slope is constant. So that slope equal to 1. Okay, and here the kilonewtons meters here. And then from here to the second segment, the slope equal to become -3. Okay, but here we can determine the magnitude 1 multiplied with 3, and so this magnitude equal to 3 here. And now we have negative. Okay, so this is -3 here. Okay, and -3 and splitting by the distance 3 here. So basically the changing from here to here should be equal to -3 times 3 equal to -9. So -9 basically downward from 3, so this value should be equal to -6 here. Okay, so now we continue. Let me change color now to so basically here is 2 here. Okay, the slope equal to 2 here, because here the slope equal to the value of V, which is constant. So here we spent with the up rising slope by distance 3, so we change from here the distance equal to should be 6 to slope 2 multiply with distance 3 should be 6, so that end up here. Okay, so that is this one. So with this information, then plug in our previous example here. So the step 2 is to determine m of x, and just like showing here. Okay, so now step 3, and plug in our equations, and 1 over rho and equal to m function of x over ei. Okay, And in general, this is the function of x, and maybe this can be function of x, but here in these chapters, we assume the moment of inertia is constant throughout the whole beam, but it can be, in general, that can be a function of x as well. The same thing for Young's modulus. Okay. So now for this case, we have the equations here. So basically for the first segment, this segment, let me call the M. Let me say this is the first segment, and the second segment is the segment. Okay. So for this case, it's pretty straightforward. That is 3 times x. Okay. So x is less than 3, greater than 0. Okay. Then for the second segment here, and m of x, you can see here the slope equal to minus 3x and then plus b here. Okay, so we can determine b. For example, when m at this location x equal to 3, the value is equal to 3 here because we identify the value here is 3. Okay, so that means minus 3 times the x equal to 3 plus b. So from here you can see b equal to 12. Okay, so b equal to 12. So that means this one is x between 6 and 3. Okay, then you can repeat the similar process to find out what is the mx for this case. Okay, let me do it quickly. So that's a 2x and plus b, and b. So again, for this case, m at this location is x equal to 9 and value equal to 0. So basically equal to 2 times 9 plus b. So basically b equal to minus 18. So basically this case is minus 18. Okay, so from here we have 3 equations. So basically here for utilizing this equation, you should depend on which sections you are interested. Then you simply utilize appropriate equation for m of x, and then follow up our next step to try to solve for the equation here. And I will keep the notes here, and if you like, you can take your time to do the screenshot for the calculations. And because the follow-up, once I hit return, and there's other information pop up. Okay, so step 2, step 3, and so by looking at those informations, let me erase the notes. And okay, so that is the information here, and so basically that is the determination of the m of x. And once we know how to solve for this equation, is basically the shape will be like this one here. And here has a few notes before we do a little bit more quantifications of the result of this equation here. Let me make a few notes, kind of qualitative descriptions of the diffraction of beam. The first one, the curvature is 0 at where the bending moment equal to 0. Okay, so again, this is a curvature, and then when bending moment equal to 0, the curvature equal to 0. So basically here, the bending moment equal to 0 here and here and here. For this case, let me change color here, here, and here. So that means the curvature at here, at here, at here equal to 0. Okay, and here we talk about the sign conventions. For sign convention, basically here, this is for this portion here, and that is positive bending. Okay, that corresponding to here. So that is positive bending. For positive bending, the beam is curved up. Okay. Otherwise, in the other remaining segment, that is downward negative bending. So that's downward. That is our sign convention. Okay. And the third one, the maximum curvature at where the moment is maximum. So that means when moment magnitude is maximum, the curvature is maximum here. So for example, here the maximum, the magnitude of the maximum moment has a magnitude here, although it's negative, but this is maximum magnitude corresponding to C here. So that is where the maximum curvature is. Okay, so that is a very simple observation of this equation here, and so we can move on. Okay, the one final point, an equation of the beam shape or elastic curve is required to determine the maximum deflection and the slope. So here I'm going to explain this a little bit more. So basically this point is more kind of relevant to how to apply this equation to determine the maximum deflection and the maximum slope there. And probably I can best describe explain this one with more examples later on. So we kind of skip this one at this moment here. Okay, so now for the remaining slides of these sections, I'm going to dedicate our time to really look into how to solve for these equations. Okay, and in particular, I want to get more information is how to get more detailed about this side, because in the previous slides we have exercise on the right hand side, in particular the moment. So we know we can apply the bending moment diagram to determine the information here. Okay, so that is done deal. So now in this section, let's look at more here. So this one basically is about the curvature. Okay, so here we look at what is the geometric the meaning of the curvature. And this one we can borrow our learning from preliminary or elementary calculus there. And if the calculus basically saying is this, we look at any curve. Okay, so maybe I can draw another one. This curve is from our textbook, but I don't like it. So we can look at here. So here we look at the two-dimensional x and y. Okay, and in this case, if we have an arbitrary curve, let me just draw it like this one, and this curve then can be described by y as a function of x here. Okay, so that's an arbitrary curve. And then here, for example, here at let me choose any point here. Okay, so that point has the coordinate x and y here. Okay, so tangent to this point, tangent at this point to the curve, let me draw that tangent line here. So that should be this one. This is a tangent. Okay, this is a tangent to this curve at this point. So for example, here this slope of tangent, usually the slope basically is dy dx here. Okay, and then for on the other side, dy dx, we also can be described as the tangent theta. So here I introduce theta. What is theta? Theta is the orientations of this tangent line. Okay, so theta we denote by theta here. Okay, so here I introduce the notation of theta. Theta simply describes the orientations of the tangent to a curve in a space. So now with the introduction of theta, I can talk about the curvature. And basically definition of the curvature simply is the changing of the theta along the curve, described by this equation. One more time, the curvature by definition simply is the changing of theta along the curve. Okay, keep this in mind in mathematics, and that's simply described as the d theta ds. And what is s? S is if you do the traveling along the curve, the traveling length is s here. Okay. So starting from the elementary definition of the curvature with the introduction of the symbol theta, which is orientation of the tangent. So let us do a little bit more. So basically d theta ds, this term I can describe putting to the multiplication of the two terms. And the way doing so, basically, if you cancel dx here, basically that ds over d theta. Okay, so let me erase unnecessary information. I keep this one here. Okay, so now for d theta dx, and with the little bit more detailed calculation can be described by this equation in green color, dx ds, and again, if here, let me skip the detail. If you take a kind of differential, the kind of calculus, and that can be described by this term. So we simply introduce the green and the blue part into our d theta ds, and after deformation, that is this one here. Okay, so that is the detail. Once you introduce the two terms, this one and this one, into the curvature, that it becomes this one here. So for this one, we look at the numerators in particular. Numerator basically is 1 plus dy dx, and we think about this one. And if I would say if dy dx can be very small, then you can see the denominator basically can be approximate as 1. Okay, so this approximation basically happened when we take the assumed dy dx is very small. So this is a very good approximation, because from here you can see the original, the curvature is so complicated form, but with certain approximation become such a easy form here. Okay, so keep in mind such the approximation taking place when we assume this one here. Okay, and this one, what regarding to our deflection of beam, what that means? So that means is this. For example, if this is our cantilever beam and its deformations, something like this one. Okay, so if you would imagine this is the curve in two-dimensional, just like I'm drawing here. If this curve, that means the deflected shape of beam. If this curve have a very small dy dx, what is dy dx? dy dx is the tangent. If this curve have a very small dy dx, that means this curve has this small dy dx, so that means this curve is pretty flat. That means horizontal. The deflection look at pretty much just like a horizontal line. Okay, so that means small deflection. So here I explained what is the small deflection in terms of the deflection of the beam. Basically, small deflection is this. And I can tell you, in most of the engineering applications, the deflection of beam basically is in this category. Okay, keep this in mind. This is a very important and practical take-home message for most of the deflections of the beams in engineering applications. They are belonging to small deflection. So under these practical considerations, the curvature can be approximated by the single term. So a curvature approximated by the single term, let me rewrite here. Okay, so this is your take-home message. So under these situations, let me rewrite here the d squared y dx squared, which is the approximated curvature, and equal to this side and x divided by EI. So this is the equations for this chapter here, and this is the very important equations. And basically, again, right hand side is about the loading information and material information. the left-hand side is the approximated curvature, and this approximation is taking place for the small diffraction. Okay, keep this in mind. So now we start from here. This is our diffraction equation here. Then here you can see in physics, this representing is the equation of deflection. In mathematics, this representing is differential equations, and second order differential equations here. And then here, if you look at this one, basically here I multiply the EI to the left-hand side, and basically become like this. Okay, and so on this side, this is called the curvature equations. And then if you integrate one more time, integrate both sides with respect to x, then you will become like this, and C1 is the integration constant. For this case, because this is the slope, so basically this equation is called the slope equation. Okay, and now you integrate one more time with respect to x on the both sides, then you will come up with additional integration constant. And from here, this one is about deflection. So basically this is called the diffraction equation. Okay, so here in terms of the mathematics, we continuously integrate twice and get the two more equations. In terms of the physics pertaining to our contents of diffraction, and usually people give a name that called the curvature equation, slope equation, diffraction equation here. So keep this in mind, and now I want to talk about more about the boundary conditions and how to solve for C1 and C2. Before doing that one, here is another important piece of the take-home message. Here you can see the C1 is a constant. Constant appear in the slope equation, so that means the C1 is a quantity that is the equivalent to slope. Slope, that means this one, so that means you need to look for is the information from theta. So to solve for C1, you must look into the appropriate boundary condition that pertaining to the slope. Okay, on the other side, C2 is a quantity appear in deflection. So C2 is a quantity that is about the deflection. So that means if you want to solve for C2, you better look for the boundary conditions that can give you the information about the deflection. Keep this in mind. We can look at more information here. Okay. So this page pretty much summarizes what we have done. So here is one example here. Okay, so here we have the C1, C2 integrations. So here we have two unknowns. Suppose we need two boundary conditions here. Okay, so the first one I tell you from the previous page, this term is the quantity regarding deflection. So here again, here we can have the free end. Here we know this is simply supported. Simply supported, that means the deflection equal to 0. Deflections equal to 0 at support. Okay, because that support that doesn't allow to displace, doesn't allow to deflect. So YA, YB equal to 0. So with the two informations, for example, YA, if you assuming say that this is the coordinate system, YA simply is Y at X equal to, Y at Y equal to 0 at X equal to 0, and Y equal to 0 at X equal to, for example, if let me assume the length equal to L. Okay, so L here. So with the two informations, then you should be able to solve for C1 and C2 here. Okay, and then let me get this one. So again, there's a similar situations. We have a supported. So this this is the overhand beam. Then again, the boundary condition is the same. The same as the previous this one here. Okay. So for this case, this is the cantilever beam. cantilever beam basically at the clamp site, and here you can find is the deflection doesn't allow to move, so equal to 0. And slope, if you can see, this is a tangent to the clamp site. The tangent equal to horizontal, so the tangent is horizontal, so that means the theta is about the slope. Okay, so theta equal to 0. So using the three examples kind of demonstrate the general kind of the steps and how to identify appropriate boundary conditions for solving C1 and C2 in general. Okay, and here we can look at one example here. So again, we're starting from our diffraction of the equations here, and here we plug in the bending equal to minus px. So how can we do it? So again, we can utilize, either you can take the free body diagrams, or you can utilize the shear and bending moment diagram. So the reaction P, and then this is a reaction bending, and bending equal to PL. Okay, so here we can draw it. So x v0, x m0. So for v, basically that is this one. So this is minus p. Sorry, bearing for my inaccurate drawing here. So now this is the bending. Okay, so this is the magnitude equal to minus PL. So at any locations, for example, here is a distance x here, then you can see the magnitude equal to minus px. Okay, the bending moment equal to minus px. Okay, so that reason we come up with this one. So we have this one, then we simply start with this equation here and minus px, and then we move the ei to here. So we integrate individually ei, dy, dx. We integrate with respect to the two sides, that is minus p x over 2 square plus integration constant. Then integrate one more time, y as a function of x equal to minus p 6x3 plus c1 x plus c2 here. Okay, so we integrate respect to x and integrate respect to x with the two equations. So now we have this one, then we look at the boundary conditions here. Oh shoot, how do I let us do this again. So that is the let's do this again, sorry. So ei d squared y dx squared equal to minus px, and ei dy dx equal to minus p over 2x squared plus c1 ei, and dy of x equal to minus p 6x3 plus c1x plus c2. So the boundary conditions we're choosing is here, and y at b equal to 0 and theta slope at b equal to 0. So that means the boundary condition is this: y at y equal to 0 at L at, let me do this one good way. So boundary conditions is this: y equal to 0 at x equal to L, and then theta equal to 0 at x equal to L. Okay, so now from this case we can see this one is the slope equations. Okay, so slope equation basically is about the theta. So from here we can see use the slope equations. So the slope equation, let me plug in the using the color here. When x equal to L, then this slope equal to 0, and then from here we can determine, that means C1 equal to P over 2 and L squared. Okay, then we can using this equation, this called the deflections equation, this called the diffractions equations here. So at here we're using information at x equal to L, diffraction equal to 0. So from here you can determine C2 should be equal to P over 6x3 minus C1x, and when x equal to L. Okay, so that one we can continue solve for that one here. Okay, so that is the equation here, and that is a detailed calculation just for your the reference. So that is a detailed calculation. And again, one more time, how this is a key step. This is a key step and for solving this kind of diffraction of the beam, because I assume the remaining the equation, solving the equation by integration is trivial. Okay, so this is the key here. So another example is the bent by distributed loading. So again, for this case, you can, the first one I want to find out what is this one here, and I prefer is the using the bending moment diagram on the other side. If you like, you can use the free body diagram here. Maybe you can try rather than using bending moment diagram, maybe we can try is this. And if you remember we have the equation. Let me think about. Okay, so we have the dm and dx equal to v. Okay, and then here we have the dv dx equal to minus omega, and that is kind of the equation for relating the distributed loading to the shear. Okay, so maybe this way we can apply this one here. So for this case is dv dx and equal to this omega equal to constant. Okay, so for this case is minus omega, and again, if you remember, the sign convention for this is positive downward. Okay, if again this is in our chapter 5. If you forgot that one, go to chapter 5 here. So basically here you can see the v equal to minus omega x here. Okay, and then let us do this integration constant. So let me call the a1 here. Okay, a1 is integration constant. So we have the v solved. So basically this one is the minus omega x and plus integration constant a1. So here we do the integration. M of x should be equal to minus omega 2x squared plus a1x plus a2 here. Okay, now we have two integration constant and a1 and a2. By looking at this information here, and we know the bending moment equal to 0 at x equal to 0 and x equal to L. Okay, so this is called the free end, and there's a free end. At the free end, no bending moment here. Okay, so by solving for this one, then we can see the a2 equal to 0. Then a1 equal to minus omega 2 times L. You can verify that one. So by plugging into this one, then basically we found the mx equal to this one. Okay, so starting from here, then we do the integration constant and then doing the whole things. And now the boundary conditions for this case is this one. This is a support here, and diffraction at A equal to 0, diffraction at B equal to 0. No diffraction because the support prevent any vertical displacement here. Okay, so that is this one. So you can look into the details and how to solve for the integration constant C1 and C2. Okay, that's a redundant, sorry, and get rid of this one here. Okay, so solve for this one, then that is the whole things. And another example, this is the overhand cantilever beams, overhand beam. And so that is from our textbook. And so from here I listed is my detailed calculations. And again, the measured rigors spent is on this. We know d squared y dx squared equal to EI and m of x. So the major effort is to obtain the bending. Okay, that is the first step. So here, this one basically is this piece, that is the minus p and over lx, and for this piece is the px and minus pl plus a. And that is the measure of the rigors you have to spend first. And this one, again, you can look at our chapter 5 contents, and there's quite a bit exercise there already. Okay, so for this case, I simply want to let you know, and here, because the m of x, that's a different expressions in this segment and in this segment. So that means here you need to separate your calculations in the two segments. So in each segment, because of the different expression for the loading information, so you have to solve for the integration individually. So here we split into two versions here. Okay, so on this side, we solve for the three things. We come up with the two integration constant. And then for the two integration constant, we must look for the boundary conditions that is pertaining to this range. So the boundary conditions you can choose for is only from, I highlight here, in this range here. Okay. So from here you can look for is one is deflection at A here, deflection at B here. Okay, just like here. So that is a valid boundary condition. You can pick it up. Okay. And then on the other side, we proceed this integration. Then we come up with the two integration constants. And again, this need two boundary conditions to solve for. And that is the boundary conditions here. And the two boundary conditions here, keep that in mind. You must choose from the boundary here, because here right now you are confined in this range. Okay, so keep this in mind. These boundary conditions must be chosen from this domain. If you choose boundary conditions outside this domain, then you are totally wrong. You are totally made a mistake. Okay, keep this in mind. So we look at here for this particular example, what kind of boundary conditions allow us to do it. So this is the information here at B. Okay, so this one you can see at B we have utilized twice, and the first one is this one. The second time we can use, because B is the common point across this point, this range and this range, in this domain and that domain. So you can use twice. That's no problem. And then here for this domain, we only have one boundary condition, but we need one more. And we need one more. How can we determine the one more equations? The one more equation basically assuming is this. Let me erase the information to demonstrate the concept here. So for this case, the beam will be deformed, something like this. Okay, so this is the diffracted shape of the beam. Okay, so now I'm demonstrating how to figure out the additional boundary conditions. Okay, we need 2 more. Okay, I'm kind of explain how can we determine the second one here. And this one can be observed by this. At point B here, assuming the beam doesn't break during diffraction. Assuming the beam doesn't break during diffraction. So that means the slope of the beam must be continuous. So at B here, this is a slope. Okay. Slope at point B is continuous. So that means from the left segment, we are able to determine the slope information. And for the beam to be continuous, the slope at the same location at B is compatible. That means it's continuous. So that means for this segment, you can utilize this information. We know the slope equal to this number here that propagated from here, and from here we got the second boundary conditions. The second boundary condition, and again, is take out this information here. So this kind of the demonstration of the big concept is allow you to take advantage of the kind of the continuity of the beam and allow you to pass information from one segment of the beam to another segment. And for this case, I think this is very useful, the information here. So here we have identified the 2 boundary conditions. So basically the 2 integration constants should be solved. So assuming you solve it correctly, then that is the case. Okay, so that is the result here. So this is an example. I simply use it to demonstrate this kind of particular approach to identifying the boundary conditions for this case. Okay. So for this case, you simply want to determine the maximum diffractions. The maximum diffraction, and this is our textbook solution here. I simply paste it here. But here the question come up with is this: how do we determine, how do we identify where the maximum diffraction could be? So here the textbook assuming the maximum diffraction happening here. If you doubt, you can also determine the diffraction here. You can also determine diffractions at you can also determine the diffraction. You can also calculate diffraction at x equal to L plus A. I think this is the L and this is A. Okay. So you can determine this one. So basically y at point C, you can determine what the number is, and for this one you compare to this number and at say y at point E. Okay, this is the diffraction at y point E. So you compare the 2 numbers, and then which bigger, that will give you the maximum. And I think the textbook skip this kind of checking, so directly tell you, okay, the maximum happened at point E here. So that is kind of the underlying story behind these things. If you doubt, you couldn't you are not sure where the location of the maximum is. If you doubt a few places, why not just go ahead to calculate the diffraction at a few places? Okay, and seems already you have the 2 equations, that kind of diffraction here. So it is easily, you should be able to easily apply the 2 diffraction equation to calculate the diffraction at any